Slides are up.
So, sound quality, let me know. I'll try to actually switch this to something else if there is. Okay. So this is our outline for today. I'll already mention it to you that this is of my video because I'm having some problems here with you don't need to see that anyways. Okay, so what I'll be very briefly a gallery of highlight sites for the HPC numerical software packages that we will introduce today, and then Alp will actually. So what we're going to be focusing on today is obviously, you know, where the agenda is located at, where you can also get slides and presenter bios. We have our hands-on lessons. You can get to the parallel breakout rooms, and there are also session abstracts. So here's just the overall agenda, which obviously is too small for you to read. So here, let me show you something that's easier to read, which gives you an overview. You have 4 parallel sessions. Each of these sessions will have like 4 different topics, and you will be able to actually mix and match. So in the mornings, the 2 parallel sessions will have a focus on discretizations for structured and unstructured, or solvers, iterative and direct solvers, so we can choose which one of those you're interested in. Then in the afternoon, we do have additional topics of nonlinear solvers, optimization, time integration, and then you can also still choose solvers if you didn't do it in the morning, either iterative and direct solvers, if that's your interest. Now, Alp will have some suggestions in case the choice for use difficulty has some suggestions. After lunch, there will be a panel with some of our experts. You can ask them questions that they will be happy to answer. And there will be a wrap up later. The subject matter experts, so the developers.
You just dropped out there for about 10 seconds.
Okay. Let me try to fix this then. Sorry about that. The problem is now I have to show them. Can't get to the meeting controls. That's the problem I'm having now. Can you hear me or not?
I can hear you.
Yes, you're fine.
Intermittent drops.
Yeah, it's just you just blanked out for a few seconds.
Okay,
before.
I think we'll just have to go with this because the only other option I have is trying to actually get out and get back in to change that. All right, sorry about that. So keep going here since we don't have that much time. Okay, you can get to our method package training here. You can see there's the intro. You do have different options here. We can get to different topics here, instructions, agenda, VIP talks, etc. Also, you can sign up for the speed dating here on this page. If you want to take a look at today's agenda and you want to find out a little bit more about the individual topics, you can go and click on these links here, and I will get you to some little synopsis. Where you can get some more information on this. Then, of course, here are the sign-on lessons under the lessons tab, where you can get to the different hands-on lessons here for the different codes. And if you want to have a small overviews of the packages, you can find them here. These are the packages we talk about today. Of course, for Zoom, I think you're all experts by now, know how to use Zoom. We want you to stay muted unless we ask you to unmute. Please use Slack for chat, not Zoom's chat. Generally, we would recommend to use the fit to window mode, actually. It's probably better. And then you can get all kinds of PDFs. And also, if you have performance issues, disable your video, just like I did right now, and stop any other streaming activity. Again, Slack, use the track 5 numerical channel here for all the presentations in the main room as well. If you need help, you can use that channel. For the breakout rooms, you should use the track 5 room name, like for example, Frontier Breakout for the Frontier room. And then please only discuss topics that are relevant to that particular presentation. And here there's also different preferences you can set. Again, if you need help, you can get it in Slack, seek for help in the Slack channel, or you can also email directly to these 3 people, Satish, Cameron, or Al. Again, during breaks and lunch, we will stay in the main room. And here is your total team. That was one of our training sessions when we were planning. We actually took that photo. So what's our goal here? We do want to make sure that you get a basic understanding of the different math algorithms, particularly solvers, discretizations, and optimizations during our presentations here. We also want to make sure that you get an overview of the different software tools that are available to you on the different architectures and give you an opportunity to practice. So we do want to kind of give you an idea on how the software really addresses the challenges for computation science and engineering, or short CSE. Give you some idea what extreme scale scientific software ecosystem are and what they're used for, and give you also idea how you can use them and contribute also. Libraries are really important for you because they will help you to not have to develop all these algorithms and implementations yourself and leave this up to experts, and also will give you a high quality product that's sustainable, and so should help you to get your scientific work done faster and quicker with good scientific software. So here again is the ATPESC team again with all the people. And I do want to kind of point you towards the VIP presentations, which will give you some more interesting talks by experts like Jim Demmel of Berkeley, Jack Dongara of the University of Tennessee, and David Keys-Koss. They're all well-known experts in their fields on different topics that are important with regard to extreme scale high-performance computing and math. So this work that I'm presenting is focused on many decades of research and development in different institutions and projects. Among those is the Exascale Computing Project, Fast Math SciTech Institute, as well as their different efforts like the Ideas Productivity Tool. If you want to learn more about productivity and sustainability, I just wanted to let you know about track 7 here, which is coming up in 2 days, so you can get more details. And over here are also various community efforts like the XSDK project, which is the Extreme Scale Scientific Software Development Kit, Better Scientific Software, and E4S, which is the software stack for the ECP actually, and they're all community efforts. You can contribute to them, have comments, etc., etc. So just a little bit more about some of these institutions. Here's the Fast Math Institute, which is the SciTech Institute. Here is a link to it if you want to learn more about it. You can click on that. It covers different technical areas. You can see many people are working there, and there's quite a bit of software there. This is just a subset of it, so there's more than that. But and then there's the ECP, of course, which really uses a holistic approach to try to do co-design and integration of these different technologies to get to exascale computing. And so it really focuses on applications, software technology, as well as hardware integration to get to the final point here. And for us, we are interested in the software technology portion, particular math libraries. That's what we are looking at. Again, CSE is the essential driver for this, and it has these 3 different areas: mathematics and statistics, computer science, and science and engineering that come together here to really help to further scientific discovery. So here I just do want to hint you to a nice article here. It's a SIME review article, which really talks about new directions toward predictive science and what role CSE really plays there. And so you can take a look at that. Again, software is really the foundation for us, how we kind of bring our research and results and developments into CSE through our particular mathematical algorithms. They're all there encapsulated in software so other people can use it, and so further science and development. So let's talk about a CSE simulation. So originally, the first goal is try to capture some physical phenomenon of interest. And so to do this, it's required to first develop a mathematical model of this, then approximate this using some discrete representation. You solve this representation with a solver, and then there's probably further application refining necessary, and possibly further physics and scales are included. And so you might have to have a loop going in here to finally get a real good simulation going. And that really requires a lot of different tools, algorithms, methods, et cetera, to deal with this, the math part as well as the architectural part and the physics part. Once you have your CSE simulation loop, then you actually want to analyze what you get. And so for that, you need additional tools like uncertainty quantification, make sure that makes even sense what you do, data analytics, optimization, design, and so on. And again, here, you require a lot of different things for that as well. So I do want to show you a very simple example of such a process, how this would work, assuming you want to kind of see how a rod behaves if it's dunked into different water temperatures, like it's a hot water bath on one side and a cold water bath on the other side. And so the mathematical model here, we have a diffusion equation here with these boundary conditions. Now we're going to use a discretization scheme by dividing this in different segments and using a finite difference, second order finite difference order approximation of this equation here. And now we can actually write a linear system by writing the individual equations for each of these points. And we get a linear system, we incorporate the boundary equations, and we can solve this. Then we can visualize the results and analyze them. And that's a very simple example. In reality, of course, this is much more complicated. So you have different discretization techniques here, for example, adaptive mesh refinement, where you might have some corners or some gaps or something that need a further investigation of that. So you want to refine, use something like adaptive mesh refinement. A lot of times your problems might be time dependent or nonlinear, so you need different solvers besides linear solvers. And then you might have a lot of different physical processes. And so you need to be very careful on how to deal with that to do it right. And so to get this all done right, you will also need optimization for uncertainty quantification. Here are some of the different efforts we will be looking at, like structured grid efforts. They focus on certain high order mapped grids and adaptive mesh refinement, etc. And so there are applications to a lot of different applications here, cosmology, astrophysics, subsurface, etc. Then also you might need unstructured grid capabilities if you have a more difficult structured problem that cannot be expressed in structure. You can have all these different issues that will come. You have to deal with load balancing, etc., architecture-aware implementations. But again, here, these are used in fusion, climate, nuclear energy, etc. Applications. Time discretization, if you have a time-dependent problem, you need to have time discretization methods. And here are some of them I mentioned here. And again, there's an application to atmospheric dynamics, ice sheets, cosmology, etc. So, and then of course, once you have these set up, you do need to have solvers underneath. Particular linear solvers, a lot of times the solver can take a huge part of the simulation. And so there are various types of solvers available. Generally, because it's a very large simulation, those systems are very large, they're sparse usually, and so you need to have different kind of solvers for that. There are direct methods available as Freilauf solvers, and we'll talk more about this in our individual sessions. Again, so that the research here involves both linear solvers as well as nonlinear solvers. There might be eigensolvers needed, etc. And all these require architecture implementation. And since they appear for all the cases we talked before, so we also find them application in a lot of the applications I've mentioned before. So what do we use to actually run these things? So here's the DOE roadmap to exascale system. As you can see, that started in 2012. At that time, we actually only had one machine that had GPUs, that was Titan. But then things kind of started to develop further here. We started to see some more. In 2018, we had more systems with GPUs. And now it looks like all the upcoming machines have GPUs, all the exascale systems for sure. Perlmutter is already there actually, but it's a pre-exascale machine, but it's not openly accessible. I think it's more for experimental use right now. Frontier is the first installation is supposed to come this year, so it's coming soon. and all the others one will come with El Capitan, the latest. So again, they do use different GPUs, you can see from different companies, and so they also require different treatment, which gives a lot of challenges to the math libraries as well the applications, because now they have to deal with all these new different architectures, which can involve dealing with different memory hierarchies, dealing with the GPUs requiring different programming models, because all of them seem to have a different programming model to make them run highly efficiently. There are issues like memory latency, communication, because we will have very many nodes for those to make sure to reach exascale, etc. And so this is very challenging. So on your end, it's really in your interest to be able to get, for us to provide you software libraries. And so there are high quality collections that help you to actually not have to implement any of these algorithms yourself. You don't have to know them. What you need to know is basically interface, how to use it, and what kind of functionality you have, how to use it appropriately. The rest you can just take advantage of the developers' expertise and their expertise with the algorithms as well as the implementation on highly complicated architectures. Here's just a collection of different of these code packages that are out there with links to it, so you can take a look at them. So here is some ECP application teams. You can see there are quite many of them, and some of our math libraries in ECP. And down here are some examples of these teams, how many libraries they're actually using. And you can see many of them use a lot of different math libraries in combination. So it's really important for them that this all works well together. As a matter of fact, multiphysics has been a primary motivator for exascale because there's so many, requires so many different mathematical algorithms underneath and discretization methods, et cetera, to be able to really run such a big multiphysics simulation that it requires the collaboration of many people. Here's an interesting article you might be wanting to read about multiphysics simulations if you want to learn more about it and its challenges and opportunities. Again, so why is this potentially an issue to have all these software packages in combination? One thing you have to remember, you just saw that some of these ECP applications use many math libraries together. And these math libraries often use third-party packages. You might have different versions, etc. So there could be conflicts there. There could be namespace conflicts if developers are not careful about their individual development, because these libraries are all developed independently, etc. And there's interoperability between them as well. And so what's really important is to look at it in terms of an ecosystem, which is a group of independent but interrelated elements. And just remember that you need to know how they all work together. So it's essentially the and when you put them together, that's important. So therefore, we really tried to build such an extreme scale scientific software ecosystem, which is the XSDK, where the focus really was to make sure it functions well together, that the quality is there, and that there's interoperability between the individual libraries. So we wanted to make sure that the code quality is there, that it's sustainable, and so on. And so that any user that wants to use an XSDK member package knows that there are certain quality standards addressed in there and that they can expect this from those. Here is the last release of the XSDK. You see at that time we had 23 math libraries. We're right now working towards a next release that should be coming up in late November again. And here are just some of the collaborators for the XSDK project. You can see we do a lot of testing, so we have a lot of people working on the testing part. But on the right, you see all the packages, you see the POCs and some of the developers. And this is just a subset, really. There are many more people who are really working on this. So this requires a lot of work. So how do we make sure that these libraries play nicely together? So to speak, we actually have a set of community policies. Here is the short version of it. So if you're interested, you can take a look on this on the xsdk.info page. You have a complete PDF there, but you can also go on GitHub where we have the individual community policies, where you can also provide feedback for us and leave comments, etc. So we do welcome feedback. That's a community effort, and it's not a static thing. We keep working on this, and we make changes to them when we see that required. So each XSDK member package will satisfy those mandatory policies and tries to do some of the recommended ones. So To build the XSTK, we use the SPAC, which is a flexible package manager that can build them all together. And SPAC actually has over 840 contributors and over 5,700 software packages. So it is an open source project. And here you can also see the complexity of the XSTK, the dependencies. Green are the member packages and black are other packages that they also call that have to also all work together. So the ECP is really the primary delivery mechanism for the math libraries there to be able to be used by the application teams. And so we do have regular releases, and we do always make sure that they work well together and try to incorporate new challenges, new programming models, having more of the libraries work together and being able to be built on different types of machines. So another important part in the ECP is actually the E4S, the Extreme Scale Scientific Software Stack. One of the things when software gets more complex, it does get harder to install tools and libraries correctly. And so the E4S is really a community effort to provide these open source software packages. So it does contain almost all the XSTK libraries, but it also has additional libraries. For example, development tools, things like MPI, etc. Data and viz tools are also part of E4S. And they do have regular, every 3 months they have new releases. They also support containers to allow applications to have pre-built packages, which can make things like a lot easier for them. The build cache has over 37,000 binaries, so it's getting huge and it's increasing a lot. And there's also doc portal, which gives you descriptions for the software products. So, and here are some more. This was some of the packages in the last release, which had 76 ECP ST products in it. They do regular testing here. There's some build pipelines here. And here's a summary of what E4S is not. It's not a commercial product, but what it is. And I'm not going to go for this for lack of time, but if you're interested in that, you can go back here and read that. So also, if you're interested in have further reading how to generate better scientific software, there's the Better Scientific Software webpage here, which provides a lot of different reading material for you to read and more than this. So if you want to learn about whatever, you can, whatever art of writing scientific software, etc., you can read about this here and other things. So now I want to get to the gallery of highlights slide, which I promised you earlier. And so I do give you, this is an overview of the HPC software packages. And so let's talk about MREX is a block structured adaptive mesh refinement framework. And you will hear more about this in the structured grid discretization sessions by Anne Alwyn and Don Wilcox later, if you choose to listen about that. Hyper is a linear solvers package, which focuses mostly on multi-grid methods. And you can hear more about this from Sarah Osborne and myself later. MFEM is it's an unstructured grid discretization tool with focus on finite elements, and the expert about that here available is Aaron Fisher. And then PETSI and Tau. PETSI is actually a collection of different types of tools, etc. And with the PETSI portion, it's focused more on the solvers. So Richard Mills will talk about nonlinear solvers here out of PETSI, and then Alp Danner will talk about Tau. That's the optimization portion. And then we have several unstructured mesh slides here, really for one product, which is Pumi. Mark Shepard and Cameron Smith will talk more about this and the unstructured grid discretization. So here are these different slides. You can look at them in more detail. Sundance is a time integration code, and Dan Reynolds will talk about this in the time integration sessions in the afternoon. So if you want to learn more about this, that's where you can go to learn more about it. And then finally, there is SuperLU, which is a direct solver based on LU factorization. Sherry Lee is the expert in that, and Strumpack, which is more hierarchical solvers, and Peter Giesels. So Sherry Lee and Sherry and Peter will talk about these in the direct solver sections. And then Trilinus is, of course, a very big package, which has a lot of different software packages underneath. So we are only focused on 2 of them here, which is Balus for the Krylov-based solvers, and this will be done by Christian Gluser, Peter Ohm, and Graham Harper later, as well as Mulu, which is the algebraic multi-grid package. I should say there are different flavors of algebraic multi-grid in Mulu and Harper. So So, and then we do have a whole list of other additional highlighted packages here, which I'm not going to say anything much about it. I'll just kind of mention them. There's ArborX Data Transfer Kit, Butterfly Pack, Jumbo, Deal 2, Ginkgo, Hefty, XFT package, Lip Ensemble, Magma, Matsumoto, Fist, Plasma, Slate, Slepsy, Tasmanian, and Zoltan. So any of these, if you're interested in learning more about them, just go in there and take a look at them. And then now we're getting to the point where we're going to the hands-on lessons. And so I'm gonna leave this over now to Alp so he can switch over to the hands-on lessons. So thank you.